Very good morning and welcome you all to this SAAO Colloquium, which is like last colloquium of the year 2021. And today we have Mattero Guainazzi from ESA. He is working in Netherlands, WHIM, and he's currently working with Athena. He has plenty of experience with working with many X-ray satellites, including XMM and Hitomi. And today he will be talking about salient features of Athena mission, which will be launched in somewhere in around 2030 plus. So let's hear from Matteo himself. Thanks for accepting our proposal of giving seminar at SAAO.
Thank you. Thanks, Sunil. Thanks for the invitation and for joining. And I am now sharing. So I'm assuming that you hear me well and you see the correct version of the presentation with only one slide. Is it correct?
Yes. Yes. Yes.
Okay, so it's my pleasure today to tell you about Athena. Is a future X-ray observatory that ESA, the European Space Agency, is studying. And the reason why I am giving this talk is that I am the study scientist for this mission. I have been in the last 5 years. But of course, this is not a talk that I prepared only by myself. Let me in particular thank in the preparation of this talk all the members of the Athena Science Study Team, which is a group of 14 scientists that are very actively working, especially in the definition of the scientific design, the scientific performance of the mission that I chair, and includes as a PI of the two instruments I'm going to describe shortly, Didier Barret for the XIFU and Paul Nandra for the WFI. So most of my talk is on the prospective Athena science, but of course I will touch also briefly on some programmatic aspects of the mission, basically when we're going to launch and why. And also, of course, I will describe briefly the main concept of the payload of the mission for you to be able to follow, the main scientific goals of Athena. So Athena is an X-ray observatory, and it's a large mission of ESA. Large means that it will cost to ESA something more than 1 billion euros, and comparable amount of money will be spent in the member state to build the instruments. So it's a huge financial undertaking, and not only a scientific and technological undertaking. Now, as any mission, Athena is being designed having a specific science case in mind. It's what we call the hot and the energetic universe, then can be summarized into simple questions, simple question with a complex answer, of course. First one is, how does the ordinary matter assemble in the larger scale structure that we see today? And the second question is, how do black holes grow and affect the cosmological evolution of the galaxy where they sit in? The first one is the hot, and the second one is the energetic universe topic. But what I would like to stress up front is that while, of course, we need a reference science case to design the mission, Athena will be an observatory open to the worldwide astronomical community, of course, including, for instance, the South African community. There is no restriction in asking time in the guest observer program of ESA missions. And so the mission is designed in order to cover a very wide spectrum of different scientific topics. And probably there is, whatever is your main source of interest in astrophysics, Athena will be able to provide revolutionary measurements to you. And in particular, it's important to take into account that Athena has been built to have fast target of opportunity capability to study transient sources, so we can repoint the spacecraft quickly if an unexpected event in the X-ray sky happens. Athena is supported by a large community, and I would like to stress also the role that an institute in Spain, in Santander, is playing in coordinating the large Athena community of more than 1,000 scientists, and also in running activities both to promote Athena in the science community and also making public outreach activities for the general public, which is the Athena Community Office. Now, which are the key elements, the key news of Athena? The first one is that Athena will carry the largest X-ray mirror for astronomy ever studied. And in on the left side of the slide, well, I'm not sure I can show my mouse, but anyway, on the left side of the slide, you see a comparison on the effective area for the Athena, one of the two instruments of Athena, with respect to existing or planned missions. And you see by eye, the scale on the y-axis is a logarithmic scale, that Athena will have an effective area, a collecting area, almost at order of magnitude larger than any existing or planned X-ray missions at 1 keV. That's why it has been designed this way. Athena will also have unprecedented X-ray spectroscopic capabilities. It will carry the first true integral field unit instrument in X-rays called X-IFU, developed by a consortium led by CNES and IRAP, with an energy resolution of 2.5 electron volts over the standard energy bandpass between a few hundred electron volts and 10 keV, which is the standard bandpass of X-ray astronomy. But this will not be just a spectroscopic capability as such. The instrument will have the instrument has a field of view of more or less 5 arc minutes effective diameter, and carries over 3,000 pixels, each of them with a size of 5 arc seconds. So as I will show you with a couple of examples later, it will be able to perform spatial resolved spectroscopy of celestial plasma, hot plasma in X-rays. And last but not least, another instrument, the Y-field instrument, is a depth-fed sensor with a CCD-like resolution of better than 107 eV at 6 keV, with a large field of view of 40 times 40 arc minutes, will be coupled with a mirror, the fastest X-ray survey machine ever designed. So I said we have 2 reference science cases that are used to design the mission. The first one is what we call the energetic universe, and the energetic universe has essentially to do with accreting black holes. Accreting black holes, supermassive black holes, also stellar mass black holes, but primarily accreting black holes from the local universe to the epoch of reionization. There are several reasons why we want a more powerful X-ray observatory to study black holes in astrophysical black holes. And let me start with one of the most fundamental relationship in extragalactic astronomy, which is the relation between the black hole mass on the y-axis in this plot and the estimators related to the host galaxy bulge mass or size. And this is a very tight correlation. There are many points on this plot which, first of all, tell us that, as we believe now, most, if not all, the galaxies, they host a supermassive black holes at the center. And this kind of relation is, in principle, a bit of a mystery, because this particular relation is with the velocity dispersion of the stars in the bulge of a galaxy. And you might argue, why should the stars in the bulge of a galaxy distributed on the scale of the tens of kiloparsec be affected by the mass of the black hole, whose sphere of influence is at most 1,000 times smaller in linear scale, at most in a linear size of a parsec or so. So there is a mechanism whereby the star formation in the galaxy is aware of the size of the supermassive black hole at the center. And what we believe now is that this relation is one of the evidence in favor of the so-called AGN feedback. So a process whereby accreting supermassive black holes, they affect the star formation in the galaxy, either because they at some point, when some sort of threshold is reached, they heat the gas of the host galaxy, preventing new stars from being formed, or because they are able, in a sense, to evacuate the interstellar milieu of the galaxy of the gas which is needed to form new stars, cold gas. So is actually this relation and evidence for AGN feedback? And one way to test it is to check, to study in detail the astrophysics of outflows that we know are generated very close to accreting black holes. These outflows are seen at several different scales, in several different wavelengths, with different energetics and properties. But if we want to check if these outflows are the messenger of AGN feedback, just looking at the simple equation of the outflow mass rate, we need to search for outflows with the largest possible column density and with the largest possible velocities. Velocity that we know in some cases are subrelativistic and can reach a fraction of the speed of light. Now we know that this kind of outflows exist. They are the so-called ultra-fast outflows that for which we have already measured very large column densities of the order of 10 to the 23, 20 to 24 centimeters square minus atoms per centimeter square. And they have also subrelativistic velocities larger than 10% of the speed of light. So X-rays are a key wavelength to study these outflows because they essentially imprint through the metals, the highly ionized metals in these outflows, signatures that are visible in X-rays, in spectroscopy in X-rays. And that's what Athena is expected to do in this field. And I show this plot, this slide, because it allows you to make an immediate comparison between the future capabilities of Athena and what we can do now with existing instruments such as XMM Newton. Now, these outflows are extremely highly ionized. This means that the main species that we're going to look at in absorption are highly ionized irons. Iron 24, either helium-like iron, hydrogen-like iron. And in the left side of the plot, you see it. Sorry, in the right side of the right side of the slide, the right side plot, you see a comparison of the spectrum that we expected to observe of Athena of the outflow in a nearby accreting black holes, PDS 456, compares with the best existing current measurement obtained with XMM Newton. And you see clearly that the red and the black spectrum, which represent the prediction of Athena, allows you to clearly identify absorption features that are completely invisible, completely blended with the continuum in current instruments due to the fact that they don't have sufficient energy resolution and they don't have sufficient effective area. So you immediately see that now it is impossible to make any plasma diagnostic using the existing lines of these outflows with current instruments. Plasma diagnostic will be possible only with Athena because it has the right combination of effective area and energy resolution. But as said, Athena will not be just a spectroscopic instrument as such. It will carry a truly integral field unit instrument. And this will allow us to perform the spectroscopy of this quality for each of the individual pixels of the XFU instrument. On the left side of this slide, you see the expected image of a known nearby AGN in the sky is NGC 5252. And the image represents the expected image of Athena of this galaxy, so the X-ray contour, the X-ray image of this galaxy. And, notwithstanding the details, you see immediately that there's lots of structure in the X-ray emitting gas close to the nucleus of the galaxy, which is at the center. And for each of the individual pixel, two examples are shown on the right side of this slide, we will be able to perform accurate spectroscopy of this plasma, which will allow us, for instance, to resolve dynamical components through the broadening of the emission lines, as now is routinely done in the optical, but it has never been possible in X-rays on extragalactic objects so far, or to study in detail the properties of plasma through the line-rich spectra that are produced by, in this case, shocked gas due to interaction between the radiation field of the AGN and the interstellar medium. So that is these two slides gives you the impression of what a true integral field union in X-ray can do in extragalactic astronomy for the first time. But we are not going to look only at AGN in the local universe. Actually, the ambition of Athena is to be able to reconstruct the whole history of accreting black holes from the local universe down to the epoch of baryonization at redshift larger than 6. Now, why is this interesting? Because we know, of course, we have known for several decades now that if you compare the density of star formation with the density of black hole accretion, over cosmic time, as shown in this plot, are the black line and the other lines. Up to redshift 2, 3, the distribution follow a very similar trend. So this is another confirmation that, you know, in the cosmological evolution of galaxies and black holes and star formation are two intimately related processes. Now, the curve in black related to a star formation is pretty well known up to redshift 6 and beyond. Well, beyond this becomes to be a bit shaky, but you know, latest HST fields they actually allow to have a glimpse of what happens beyond 6. Whereas as the difference, the variance of the curve on the other colors in this plot shows, the density of accreting black holes at redshift larger than 3 is extremely uncertain. And in order, you know, one of the goals of Athena is actually to nail down the history of evolution, the cosmological evolution of accreting black holes by measuring a sufficiently large number of AGN at each redshift. Now, we're not just looking of any kind of AGN. There are some specific phases of AGN that are particularly crucial in order for us to understand and highlight the relation between the evolution of the host galaxy and the evolution of the accreting black holes. The left side plot in this slide showed, you know, a synthetic view or an artistic view, if you like, a semi-scientific view of the evolution of a black hole hosting a galaxy depending on the halo mass, high, medium, and low, as a function of cosmic time evolving from top to bottom. And essentially, notwithstanding the details, there are two crucial phases in the evolution of a galaxy hosting an AGN that are still not very well understood due to the lack of data. The first one is shown in sort of brown or dark magenta color, which is a phase when, after the merging of two gas-rich galaxies, we have the generation of an ultra-loop of a very infrared-rich single galaxy, merged galaxy, hosting an extremely obscured AGN at the center. At some point, this AGN activates, or actually supermassive black holes activates. This probably creates relativistic or semi-relativistic jets and outflows that actually can clear the gas in the environment of the host galaxy and allows us to see the optical, infrared, and also X-ray phase of the quasar, which in this plot is represented by the big blue star. Now, these phases are relatively poorly known because we don't have very large samples of heavily obscured AGN or AGN with extremely relativistic outflow that has been seen at this redshift between 1 and 4. But Athena will allow us to cover this gap because it will have sufficient sensitivity to detect a large sample of heavily obscured AGN in X-rays to the level of being Compton thick, because they have a typical X-ray spectral signature that is, you know, most notably the very strong iron line showed in the top right panel of the slide, as well as object with very strong outflows at redshift larger than 1. And so far, strong outflows have been seen in X-ray spectroscopy only in the local universe. This will be possible because Athena will detect several hundred of thousands of AGN over the whole redshift range from the local universe to zeta of the order of 8. In this plot on the left side of the slide, I compare the luminosity in X-rays with redshift for several samples. The black dots represents the current XMM Newton and Chandra surveys. The orange contours represents eROSITA, which is an X survey missions that is now currently running and that is expected to produce a sample of 3 million of AGN, which is of course an extremely valuable resource, but as you see from this plot, this will still be limited to AGN in a relatively nearby universe up to redshift of the order of 3. And the green points are the expectation of the distribution of AGN in this plane to be seen by Athena. And the important point is not only that we will observe AGN up to redshift 8, but they will have a luminosity of the order of 10 to the 43, 10 to the 44, so luminosity equivalent to those that of Seyfert galaxies in the local universe, which will allow us to constrain efficiently the seeds, the black hole seeds in at redshift 10 that are responsible for the generation of supermassive black holes in the far universe. And that's why Athena is revolutionary with respect to any other planned or existing mission, because it will be able to probe an unprecedented parameter space, both in redshift and in luminosity. But at the same time, Athena will be also an invaluable resource in order to detect extragalactic transient objects. So, you know, we have so far mentioned objects that are always visible in X-ray skies, but we know there is lots of transient event in the sky, in the X-ray sky, that can convey unique information that has been impossible to probe so far. This will be possible because the spacecraft of Athena will essentially be able to repoint in whatever position of the sky within its field of regard within maximum 4 hours. And given the field of regards, we expect that this will be possible about 40% of the cases if we assume a random distribution of transient events in the sky. And the events that we're going to observe with the highest priority are high redshift gamma ray burst afterglows. We expect to be able to determine on GRB afterglows the spectra of the interstellar medium of the host galaxy of the quality shown in the top red side plot that I'm now showing with my mouse, which will allow to unveil the interstellar medium composition at redshift larger than 7. And just to stress that this kind of galaxies are galaxies that will even very difficult to be observed for JWST. So these will be extremely powerful probes in order to investigate the composition of the ISM in the early universe. And another field where Athena will surely create extraordinary new results are tidal disruption events. So those events that are the results of destruction of a star by a supermassive black holes, which allow to unveil quiescent supermassive black holes, reveal the composition of the outflowing material, possibly detect the QPOs as recently demonstrated in a paper just published a few weeks ago, and also test for the presence of binary supermassive black holes in these systems. Let's go now to the topic of the hot universe, and the topic of the hot universe has to do with the evolution of baryons from the epoch of formation of large A structure to the local universe. So we all know that universe on the scales larger than gigaparsec is not up to the gigaparsec is not homogeneous, and the visible matter, the matter emitting electromagnetic radiation, is not distributed randomly, but is distribution along filaments that are shaped by the gravitational potential of the dark matter. And we know that this kind of structure start forming around redshift 2 to 3. And we know very little about the astrophysical and physical properties of the baryons in the universe at this redshift. And the reason is that cosmological simulations tell us that most of the plasma in these filaments is actually in a very hot phase with a temperature of the order of larger of 1,000,000 degrees. So temperature or the order of larger of 1,000,000 degrees means that this plasma emits primarily in X-rays. So if we want to investigate the baryons, the properties of these baryons on this scale, we need to have a very powerful X-ray observatory, and Athena has been designed for this purpose. In particular, we are going to look at the nodes of the cosmic web, where the largest gravitational bound structure in the universe, galaxy groups and galaxy clusters, are located, and we hope to be able to create with Athena spectra of the intercluster medium of galaxy cluster of the quality shown in the right side plot of the slide, which represents an expected result of an X-ray view observation of a nearby cluster in the local universe, the Perseus cluster. Now, just to give you a glimpse of what these measurements will represent in terms of improved performance with respect of existing mission, I show you a comparison of a spectrum obtained, the only spectrum of a galaxy cluster obtained by the Japanese mission Hitomi with its instrument SXS, compared with the spectrum that on the same target was obtained by another Japanese mission, Suzaku, with the CCD instrument. The CCD instrument is a red curve, and the microcalorimeter measurements is the black one, once again in the key energy range corresponding to iron transitions. And you know, one doesn't need to be a specialist in spectroscopy to understand that basically no real diagnostic was possible with the red curve spectrum, and diagnostic is now possible at an unprecedented level with the black spectrum. Now, you may say, why are you showing that? Does it mean that the measurements that Athena is going to perform has already been done? Well, this is unfortunately the only spectrum of this quality that this mission was able to generate, because the mission failed 6 weeks after launch due to a mishap in the attitude control system of the spacecraft. And therefore, in this moment, there is only one spectrum in the archive worldwide of this quality. So Athena is going to make a giant leap, not only because the spectra of this quality in the local universe will be routinary, but because for two main reasons. Because we will be able to create a spectra of this quality on spatially resolved structure. And this is an example of a simulation on the left side of, for instance, a metallicity map that we expected to obtain with the WFI on one of the nearby cluster in the local universe. And you can see from the details of this image, whose size is 30 arc minutes, corresponding to 20 kiloparsec intrinsic project linear size, you see that we will be able to perform extremely accurate measurement of the metallicity on scale of the order of few arc seconds, corresponding to a few kiloparsec of this giant structure, encompassing hundreds, if thousands of different galaxies. But more critically, Athena will be able to extend this study to redshift 1 and beyond. And this is important because it will allow us to perform plasma diagnostic of the baryons locked in the intercluster plasma of galaxy clusters at the epochs where these structure formed, and therefore study the evolution of the astrophysical properties of this plasma from the epoch of formation of this structure to the current universe. And the right side plot shows you the comparison of the expected Athena X-ray view spectrum of a galaxy cluster at redshift 1 with the current measurement with XMM Newton and the current measurements of an Hitomi-like mission. We will have soon an Hitomi-like mission called the CRISM to be launched by the Japanese Space Agency. But you immediately see that this mission, while extremely powerful in the local universe, will not be able to make any reasonable measurements in the high redshift universe. And once again, the difference is not only the spectroscopic quality, but also the fact that with Athena, we will be able to perform true IAFU measurements, so true spatially resolved spectroscopy. And I compare here the image of the Perseus cluster obtained by Hitomi with the spectrometers on board Hitomi. And the spectrometer had 35 pixels on a total linear size of 3 arc minutes. So each pixel had a size of 30 arc seconds. And of course, you can do some spatially resolved spectroscopy, but very limited. Whereas the simulations that I show in this slide, they represent maps of the bulk motion velocity of the abundance of various elements that you expect from a similar cluster as those observed by Hitomi in its only single measurements. And you see the enormous amount of detail at the scale of arc seconds that Athena will be able to create on all these parameters. That, of course, describes the physics and the astrophysics of the baryons in the intercluster medium. And just to reiterate, we will be able and therefore to measure very accurately, for instance, abundances of the intercluster gas. This is shown in the left side plot, where the accuracy on the abundance measurement for various elements from oxygen to iron is shown as a function of redshift. And you see that we will be able to obtain abundances accurate to the level of few percent, or at the worst, accurate at the level of 20% for calcium at redshift 1. And not much worse at redshift 2. And the fundamental astrophysical reason why these measurements are important, because these actually allow us to pinpoint the cosmological evolution of the source of astrophysical events that produce these metals. We know that the metal abundances in the intercluster medium are a source of integral over cosmological timescales of different type of process, subtype of supernova remnants, or for some very low zeta elements of AGB stars. And by measuring abundances, we can reconstruct very accurately what fraction of its element is due to each process, to AGB stars, to core collapse supernova, or to 1A type supernova. And these measurements will be able in the local universe at redshift 0.1, but also in the far universe. So immediately you see the power of these measurements, not only for constraining the evolution of the baryons that we see, but also to constrain the unseen history of the supernova explosions in galaxies down to high redshift. We will also be possible through measuring the entropy profile of galaxy group and galaxy cluster at high redshift to measure whether the heating of the gas during the accretion phase is due only to gravity, or there are feedback processes like a supernova remnants of AGN that contributes to the process. And this will once again highlight the processes by which the baryons locked in the intracluster medium of galaxy cluster or intragroup medium of galaxy groups evolve over cosmological timescales. Now, we know, of course, from very deep measurement with Chandra in the local universe that AGN feedback exists in galaxy cluster, is so-called radio mode feedback, essentially due to relativistic jets emitted by the large radio galaxies, the center of each galaxy cluster. Very deep imaging with Chandra highlighted the presence of cavities and bubbles that are undoubtedly due to the effect of prior phases of AGN activity in the center galaxy. This is known because we can correlate the power needed, for instance, to evacuate a cavity with the integrated power of the AGN measured from the cooling luminosity of the synchrotron emission. And of course, these images, the one I show on the left side, exist. They have been taken by Chandra. So we can do very accurate imaging of this phenomena, of this radio feedback phenomena. But the effective area of Chandra and the energy resolution of Chandra do not allow us to perform any microphysics measurements of the processes that occur in the cavity, at the border of this cavity, so where actually these interactions occurred. But this will be possible with Athena, because being once again Athena and truly EIFU, we will be able, for each of these systems where cavity and bubbles and ripples are seen, to perform accurate spectroscopy of each individual pixel. And by studying, for instance, the energy and the shift of the iron lines which are emitted by the million degrees plasma in this system, we will be able to study the role of thermal versus non-thermal processes, because we will be able to measure directly bulk velocity and turbulent velocities. And of course, we'll be able to study metallicity, and we will be able to study the temperature of the plasma on unprecedentedly accurate spatial scales. Another thing that we hope to address definitely with Athena is the issue of the missing baryons. We know from cosmological simulations that 50%, or we expect from cosmological simulations that 50% of baryons in the intergalactic medium should be locked in a very hot phase with temperature between 10 to the 5 and 10 to the 7, so let's say million degrees of temperature, once again a typical temperature of X-ray emission, but they have escaped the detection so far. And the way they can be detected, there are two ways. Either they can be detected as absorption features, absorption system against a bright background source, that could be an AGN or a gamma ray burst afterglow, or in emission. And 40% of these baryons are still escaped clear detection, clear observational detection. So we hope to be able to see them in X-rays. Now, we have been unable to see them in X-rays so in this moment because simply we don't have a sufficient effective area to measure these very tiny features absorbed in emission or in absorption. But with Athena, this will be a no-brainer. It will be extremely easy given the large effective area and the energy resolution of the X-ray view instrument to detect the signatures in the soft X-ray band of the WHIM, of the warm hot intergalactic medium. And actually we plan during the 4-year observational, nominal observational life of Athena to observe basically 200 systems in absorption and some of them also in emission once the absorption measurements tell us which is the best system to point to. And the right side plot shows, it's a bit a complex plot, but it shows the density of oxygen of the WHIM that we expect to measure as a function of the X-ray flux. And this plot essentially drives the requirements on the speed of the reaction time of the spacecraft to gamma ray burst. Essentially, we want to be able to go to very quickly, within 4 hours, to a gamma ray burst in order for us to be able to constrain through spectroscopy the density of the oxygen features at the level which is correspondent to a few, and I can see the scale of the plot on this. Okay, well, corresponding to of the order of the critical density of the baryonic matter in the universe. Now, as said, these are the science cases that we use to design the mission, but Athena will be an observatory. You as an observer, you will decide what Athena is going to observe and which science is going to be made. And the science case of Athena involves a large number of possible measurements on system going from planets to exoplanets to region of star formation, massive stars, supernova and supernova remnant, interstellar medium. There is basically no corner of astrophysics that would not be affected by an instrument with revolutionary combination of proper scientific performance. And in particular, the ambition is that Athena will be the X-ray mission perfectly matching the large-scale multi-wavelength facilities that will be available in the decade of the 30s. From SKA to the radio, to ALMA, to a speak-alike mission if existent, to JWST, whose launch we are looking forward to in a couple of weeks, to the large ground-based telescope. Athena is actually, the sensitivity of Athena is well matched to all these facilities, as shown in this plot that show the expected spectral energy distribution of an ultra-luminous infrared galaxy and obscured AGN in the local universe brought to redshift 7, and you see that the Athena sensitivity perfectly matches the sensitivity of the other facilities to detect the sources of this kind that are key for our understanding of the connection between accretion and star formation in the early universe. And this is due to the fact that Athena will have a revolutionary mix of science performance. So Athena represents an order of magnitude improvement on several parameter spaces simultaneously. Just as an example, in this plot, I show on the x-axis the weak line sensitivities as 1 kV, ensured by the X-IFU instrument, so by the spectrometer, against the point source sensitivity on the y-axis, which is essentially due to the collecting area of the telescope. And you see that comparing Athena with existing missions and also planned mission in the future, Athena is 1 order of magnitude more proficient, more performant in both parameter spaces, and therefore there is no telling which kind of new science Athena will be able to enable once launched. And just a couple of figure of merit, more in practice. This is a comparison of the effective area for the XIFU instrument and the WFI instrument, once again, against the planned or existing X-ray mission carrying instrument of a similar quality. And you see that the difference in effective area at 1 kV, where the mission has been designed, is at least 1 order of magnitude, and also 2 order of magnitude for the XIFU. As far as the spectrometer is concerned, this translates in a weak line sensitivity with respect, for instance, to the similar mission that JAXA is going to launch in a couple of years by more than 1 order of magnitude. And another kind of illustrative comparison is the one on the right side of the plot, where I compare the expected Athena XIFU spectrum of the Perseus cluster with the marvelous spectrum obtained by Hitomi that I showed you a couple of slides before. You know, if you were impressed by the quality of the spectroscopy obtained by Hitomi with respect to CCD spectroscopy, imagine what an instrument like the Athena XIFU will be able, by delivering a number of counts per resolution element more than 1 order of magnitude larger than any existing or planned mission. And the WFI, as said, coupled with a telescope, is a very powerful survey machine. Athena will have actually up to observation deep of the order of 1 megasecond, so several weeks, an average flux sensitivity over the whole field of view better than Chandra, even if Chandra has an extraordinary angular resolution and therefore is able to, for instance, cut the background level to ridiculous levels. The fact that the PSF, the point spread function of the Athena optics, will be basically constant over the whole field of view, whereas the point spread function of Chandra degrades rapidly over the field of view, makes actually Athena a competitive survey machine, even with respect to Chandra. And this is shown in the right side plot of this slide, where I compare the number of sources detected in 100 kilosecond observations by Athena. These are the yellow and magenta curves corresponding to slightly different possible configuration of the instrument, against Chandra and XMM Newton. And once again, Athena will be able to detect 1 order of magnitude more sources per each individual observations. And when I mentioned that we will be able to measure 400,000 AGN, this number refers to the nominal 4-year mission. But if Athena continues as technically possible for another decade, the number of new X-ray sources that Athena will be able to discover will exceed a few millions. And so it will be an enormous resource for generations to come. So that's essentially the last slide of my talk. I hope I convinced you that I'm working for a revolutionary observatory in terms of science performance and expected science results. So we hope and we're sure that Athena will be a transformational X-ray observatory. Once again, I want to stress a key message that it's designed to address 2 specific science teams, because engineers need a science team in order to design the mission against. But it will be an open observatory that will impact virtually every corner of astronomy, and it will be the community to decide which corners will be the most impacted. It will be an essential part of the observational landscape in the 2030s, together with existing or planned large-scale ground-based or spaceborne facilities. It has already a community supporting it of over 1,000 scientists who are already working very actively to support the design of a mission and help ESA in advising on the best trade-offs in order to optimize and maximize the scientific outcome of the mission. And the current situation is that we are in a design phase called phase B1. And the next key milestones is a process called mission adoption, which is the point of no return of the mission in the ESA science program. That will happen in February 2023, in 1.5 years from now. And after that, an implementation phase of about 10 years is foreseen for a launch in 2033. And if you want to know more of Athena, of course, I'm glad to take now any questions you may have. You are, of course, welcome to contact me at any time in the future. But the work done by the ACO is extraordinary in providing a set of resources on the mission. And you are, of course, very welcome to look at the Athena presence on the web and on the social media. And with this, I thanks for your attention, and I'm glad to take any questions.
Thanks a lot, Matteo, for this fantastic talk. And there are a couple of hands which are raised, so I would request David to start.
That was a great talk, Matteo, and it really looks like to be quite an amazing mission. I have a technical question about the IFU X-ray spectroscopy and how that's achieved. I presume it's because you have energy resolving pixels or detectors. Is that correct?
Yes. The technique, I didn't delve too much in the technology, but essentially this is a microcalorimeter system. So each pixel is constituted by an absorber that essentially, absorb an incoming photons. This absorber increases slightly the temperature, and the way the temperature yield a change in the resistivity of the semiconductor, which essentially allows you to reconstruct the energy of the incoming photons by measuring this very small change in temperature. So these are cryogenic instruments that have to function at 50 millikelvin because the difference in temperature are extremely tiny. But of course, this is a kind of technology that has already been demonstrated to be feasible in space. In fact, the microcalorimeter on Hitomi was based on the same kind of technology. The challenge is that the XIFU, a very large instrument, it requires a very large dewar, and it weighs by itself 800 kilos. But notwithstanding these small details, is a quite robust technology.
Right, and I guess it's quite different technology to something I was more familiar with over 10 years ago, these superconducting tunnel junction type detectors that ESO were looking into.
Yes,
and I guess this is completely different because they're not producing Cooper pairs or anything like that. It's just very accurately measuring temperatures. Is that right?
Yeah, that's correct. It's actually, the trick is measuring very accurate temperatures, and this allows you to correlate very, very precisely with the energy of the incoming photon. That's the trick.
Thanks.
So, Hermod, please unmute and ask question.
Yes, I was interested in your AGN spectra that you are planning to do. Roughly how many, since you look, it's part of like a systematic program, how many of those do you expect you'll be able to do, say, a year? Something where you, and how long is each typical such integration? Is it like an hour? Is it longer?
It's a typical integration is a day. And so we have, of course, what we call the mock observing plan. So we have already a list of the sources that we may observe covering the nominal mission. And I can tell you, for instance, as far as the bright X-ray AGN are concerned, we have of the order of 70 objects in the plan, each of them observed for 1 day or so. So each of them able in principle to deliver a spectrum of this quality. Okay, and this is only for the nearby AGN. On the other hand, as far as the, let's say, more high redshift AGN that will be discovered in the X-ray survey, I went maybe a bit too fast here, but for instance, in the case of high redshift AGN, we expected to observe more than 150 at redshift larger than 6, and we expected to have of the order of 50 to 100 heavily obscured AGN in the redshift range between 1 and 4. And these will be obtained through this, through a survey of the sky, looking at several square degrees of the sky in the 4 years.
Okay, thank you.
So since I don't see any other hand raised, so David, you can ask again. I think you wanted to ask something.
Yeah, I should have asked in the original question, but is there any time resolve capability with Athena? I mean, what's
yes.
the fastest sort of time resolution you can get?
Milliseconds.
Oh, really? Okay.
Yes. The timing capabilities, I even didn't mention it because it's a standard for X-ray astronomy nowadays, but essentially both instruments have a millisecond capability, and actually the WFI, once again, it was a bit of a detail, but the WFI will actually be constituted by two independent detector systems. One is the large field with 40 arc seconds array, and this will have a time resolution of 5 milliseconds, if I remember correctly. But then there will be a small chip, the fast detector, which essentially is a tiny thing of 2 arc second time 2 arc second, 2 arc minutes, sorry, time 2 arc minutes field of view, but it will have a time resolution of 80 microseconds, and this is intended for very fast readout of bright sources, essentially X-ray binaries.
Right. Well, you mentioned X-ray binaries, but on your last slide, or one of your last slides where you had all of the different other sort of themes, I didn't see it mentioned. Which
yeah. No, you're right, and that's okay. That's a mistake because, well, essentially, X-ray binaries for us are core science, and they belong to the energetic universe.
Okay.
So I had in the prior version of the talk a specific slide on X-ray binary under the energetic universe. Then I remove it, and I forgot to say, well, but in this case I never mentioned X-ray binaries. But no, of course, is one of the key science cases of Athena, and it's driving a lot of the design of the mission because. Observing very bright sources of the order of fraction of a crab or more than one crab flux is very challenging. Yeah. But yes, they are a core part of a core science of Athena.
Great, thanks.
Matteo, since you just talked about binaries, and my question is like, what will be your comment about expected revolution in disk reflection in spectroscopy of X-ray binaries and ASIANs, which
it's interesting because it's another cases that I did not mention, not because Athena is not going to do anything on it, but because we consider even it in a sense too easy for Athena. But what we expect to do is to be able to, of course, for all these 70 AGN and in the nearby universe, for instance, we will be able to perform the extremely accurate measurements of the profile of the relativistic profile of the iron line, and also, of course, measuring in an extremely accurate way the soft excess. So we expect that during the nominal operations, so the 4 years, to measure black hole spin for nearby AGN on at least something like 30 AGN, with the potentiality actually to get good measurements on all 70 of them, and maybe others serendipitously. So to have, let's say, of the order of 50 to 100 measurements of the black hole spin in the local universe through X-ray spectroscopy. And this will be due to the fact that we will be able, of course, to fit extremely accurate data with extremely accurate models. Now, the reason why I've not mentioned it upfront is that this will be, of course, extremely interesting. However, since we know now what we didn't know, of course, at the time the Athena proposal was made, that gravitational wave exists. Now we know that we will be able to measure spin in AGN very efficiently also in gravitational wave. So it's a bit arguable in the community whether X-rays or gravitational wave in the long term will be key to measuring spin of black holes in AGN. Because LISA will be launched a few years after Athena, and they will be able to measure spins over the whole cosmological history of the universe. But Athena will be launched first, and for sure, the first distribution of black hole spin in the local universe will be done by Athena, no doubt. Then LISA will overtake and overwhelm us, but the first real measurements will be done by Athena.
Perfect. Thank you. Yeah. So we can have one more question if anybody want to ask. Okay, perfect. So now this was really very nice presentation and a lot of crucial information about Athena mission. And we hope that this will revolutionize entire energetic universe, actually. Thanks a lot.
My pleasure. Thanks for your questions, for the feedback.